Welcome all of you. In the last class, we discussed about chemical shifts, last two classes precisely. We understood a lot about chemical shifts, how it comes, what are the factors which govern the chemical shift, how different functional groups affect it, how do you measure the chemical shift, the references that we are going to use, how do you express chemical shift in ppm, how do you convert ppm to frequency and frequency to ppm, varieties of things we understood. We also understood about the factors that govern the chemical shift, what happens if there is a electronegativity group substituted, how do the chemical shift changes from low field to high field or high field to low field depending upon the electron is donating or getting withdrawn. We understood the mesomeric effect and what happens because of the benzene ring current, what happened to the proton situated in the plane of the ring and what happened to the proton situated above and below the plane of the ring, how they are shielded, where they are coming, whether it is shielded or de-shielded, all those factors we understood. And we also said the chemical shifts is a fingerprint for a given molecule, different functional groups where it comes, by and large is well known, and there is a chart available for different nuclei, not only for proton, for fluorine, carbon, all those things I did not show, but varieties of nuclei charts are available. If you are looking for the fluorine, if you want to look for CF3 group present, where it is available, where generally it resonates, look at the chart, you will get the approximate range. From that you can utilize as a guideline and start the analysis. That is how it chemical shift can be utilized, and we understood a lot about chemical shifts, but there is no time to discuss much more. But today we will introduce another parameter, internal interaction parameter, which I said called scalar coupling, which we discussed earlier. So, now the scalar coupling, it is called spin-spin coupling, as the name clearly tells you, it is the interaction between two nuclear spins. Each spin is a tiny magnet, one magnet can interact with another magnet together, and this interaction is because of the involvement of the electron surrounding it. That means you consider CH proton, CH bond, there is a carbon, this nucleus surrounding electrons, and this also has a nucleus surrounding electron, this electron in turn interacts with this electron and in turn this interacts with nucleus. This nuclear spin interacts with this nuclear spin, where the magnetization or the spin polarization is transferred from one nuclear spin to another nuclear spin through covalent bond, through the chemical bond. This is an interaction between two nuclear spins mediated through covalent bond. It is a magnetic interaction. This is one of the important interaction which are responsible for giving rise to multiplicity of different functional groups. See, in the chemical shift we did not discuss about multiplicities. You will see a peak, let us say without any coupling you will get a single peak, but once the one proton interacts with another proton or interacts with number of other protons, then we are going to get the polarization transfer taking place between one proton and other proton depending upon the extent of interaction, strength of interaction, and we get different multiplicity patterns. That is what we are going to understand today, how the spin-spin coupling comes, how the multiplicity pattern gets affected. So, this is the major concept. Remember, spin-spin coupling, it arises because of interaction between the two nuclear spins mediated through covalent bond. Without going into the more details, let me tell you something about the salient points of the scalar couplings. Scalar couplings are generally represented by Jij. I and J are the two interacting nuclei. Always we discuss about interacting between two nuclei. One nuclei can interact with many other nuclei, no problem, I will show you that now. But any two interacting nuclei I and J, the interaction strength, the scalar coupling is given by Jij. Now, these are the few points you should remember. First of all, it is a covalent bond mediated interaction, it is not a through space interaction. Consider a molecule like this. Now, this proton can interact with this proton through covalent bond like that, okay, and this proton can interact with any of these proton or all the three protons through bond like this, and there is no way it can interact like this, okay, there is no way it can interact like this, that is not possible. This is a through space interaction, that is a dipole interaction, which is a different thing which we are not discussing. But scalar coupling is always mediated through covalent bond, it has go only through bonds. and J coupling is denoted by NJIJ, where N is the number of intervening bonds between the two spins I and J. For example, in this case there are two intervening bonds, in this case 1, 2 and 3, there are 3 bonds intervening between these I and J. Okay. And J coupling depends on the electron charge density at the nucleus and are not averaged in solution state. Remember, J coupling also depends upon the charge density at the nucleus, but they are in the solution state, they are not averaged out unless dipolar couplings. That is why they are not going to depend upon orientation of the internuclear vector, hence they are called scalar couplings, because they are not orientation dependent. Internuclear, it does not depend upon the orientation of the internuclear vector. As a consequence, J coupling is called a scalar coupling. It is just a number, and the strength of the interaction always varies from few hertz to few tens of hertz, of course depending upon the nuclear of your interest. If I consider 2 protons, depending upon the number of bonds they are separated, the coupling constant can be different. It can be few hertz to few tens of hertz. For heteronuclei, it is even more larger. There are examples in some exotic nuclei, the coupling constant could be very, very large, of the order of thousands hertz. It is possible, several thousands of hertz, that is also possible. But remember, for proton when we are talking, it is few hertz to few tens of hertz. And the coupling interaction between spins can extend between 1 bond, 2 bond, 3 bonds, any number of n bonds. But only thing is, as this number of bonds increases, the strength of interaction keeps coming down. Here it is a 2 bond coupling, it is represented as 2JHH. This is stronger. Go to this one, this is 3 bond coupling, little weaker. This is 4 bond coupling, 5 bond coupling, this is 5JHH, this is 6JHH. So, as the number of bonds increases, strength of interaction reduces drastically, but nevertheless this single proton can experience coupling between varieties of proton which are separated by several bonds also simultaneously. If it experiences coupling with this, it does not mean that there is no coupling with this, it can simultaneously experience coupling with all the protons. Only thing is, strength of interaction is different depending upon the distance they are separated, how many bonds they are separated. And this value of the coupling can be always positive, negative and 0 also. If there is a coupling between this and this, it could be, let us say 10 hertz, it could be 10 plus 10 hertz or minus 10 hertz. Coupling could be 0 also, all are possible. It could be positive, negative or 0. Strength of interaction can be different. And coupling can be between homonuclear and heteronuclear. When I am talking with proton, that does not mean it should interact with only protons. It can couple with any other nuclei which is present in the molecule. Take for example this group, an hypothetical group I am taking. Now there can be a coupling between this proton and phosphorus, 1 bond pH coupling is present. There is also possible between coupling between this proton and this proton, 2 bond pH is also possible. This coupling is present. You look at this molecule. Now I can expect coupling between this proton and this proton separated by 3 bonds. The proton to fluorine is possible. Carbon to proton is possible, separated by 2 bonds. And carbon to carbon 1 bond coupling is possible. Carbon to fluorine 2 bond coupling is possible. And fluorine to fluorine 5 bond coupling is possible. And fluorine to proton coupling 3 bond is possible. See, varieties of coupling is possible. It need not be homonuclear. Coupling can be between homonuclear spins and also heteronuclear multiple spins. And coupling constant is just a scalar quantity. It is only a magnitude. It is just a number. You do not have to give any unit for it. If I say there is a coupling constant, we just say a hertz, 10 hertz, but it is a number. You should always know it is a hertz. It is expressed in hertz, it is just a number. The magnitude of the spin-spin coupling between the coupled spin decrease with the increase in the number of bonds, that is what I told you. 1 bond coupling is larger than 2 bond coupling, than 3 bond coupling, than 4 bond coupling. But it is a general trend, there can be exceptions. You can't come and say tomorrow, okay, 2 bond coupling is smaller than 3 bond coupling, it is possible. There are many examples like that. Many deviations are possible in NMR, but remember this is a usual trend. Usual trend is as the number of intervening bonds increases, the strength of interaction keeps coming down. And the coupling constants are independent of the applied magnetic field. It's a very, very important point one should remember. Remember I said chemical shifts depend upon the magnetic field. They vary linearly with the magnetic field, whereas the coupling constants are independent of the applied magnetic field. You record the spectrum today in one spectrometer. Let us say coupling constant is 10 hertz in a 300 megahertz spectrometer. Go and measure it 500 megahertz, 800 megahertz or 1000 megahertz, no problem, coupling constant remains same. Whereas the chemical shift will be linearly changing, but coupling will not. Okay? Coupling constant is independent of the applied magnetic field. And the splitting patterns are independent of the sign of the coupling constant. That is another important thing. Let us say I have a coupling, there is a 2 lines because of the coupling I am going to see and measure this coupling as 10 hertz. Even if I make 10 hertz, it remains same, pattern remains same. Only thing is this line comes here, this line comes here, but the pattern will not be different. The splitting patterns are independent of the signs of the coupling constants. And one spin can simultaneously experience coupling with many other chemically inequivalent protons or inequivalent spins, not necessarily proton, it could be heteronuclei also. And the coupling can be different strengths. Very interesting point, please understand. Very interesting thing is only consider any one proton or any one spin in a given molecule, then that particular spin can simultaneously experience couplings with many other chemically inequivalent spins. Consider let us say proton here, this is highlighted in red color. This proton can experience one bond coupling with this carbon, one bond coupling of CH is quite large. It can experience 2 bond CH coupling which is much smaller. It can experience 3 bond coupling with fluorine. It can experience 3 bond coupling with this carbon, this is much smaller. It can experience 4 bond coupling with fluorine, phosphorus, not fluorine, I am sorry, phosphorus. It can experience 4 bond coupling with this carbon. It can experience 5 bond coupling with this fluorine, and it can also experience 3 bond coupling with this proton and experience 3 bond coupling with this carbon and 4 bond coupling with this proton. See varieties. Remember this single proton can experience 10 different types of couplings, both homo and heteronuclear, and all these coupling strengths could be different, they need not be same. One may be 10 hertz, other may be 100 hertz, other may be 500 hertz, no problem. But they simultaneously this proton or any particular spin if you consider, if there exists an interaction, it can experience couplings with varieties of spins simultaneously. And there are also, as I was telling, always the coupling is through covalent bond, but there are some typical examples like this, molecules like this, there is through space coupling is possible. It is because if one of the atom has lone pair electrons and if the 2 interacting nucleus are very close by within their van der Waals radii, then what will happen? You can see the coupling between these 2 directly without going through covalent bond. This is called through space coupling. These are all exceptions, okay, but it is not covalent bond mediator, remember. Now one peak from one spin coupled to other chemically inequivalent spins split into multiplicity of peaks. For example, one proton is there, it gives rise to a single peak. It will each coupled partner splits the peak into 2 peaks. Let us say it is coupled to another proton, it will become doublet. Another single proton which is present makes the single line into 2 lines of equal intensity. Now it is coupled to let us say another proton. What will happen? 2 lines will become further 4 lines, 2 lines of equal intensity. Each of these 2 lines will become another 2 lines of equal intensity. Again if there is another proton, further split into another 2 lines of equal intensity. But remember the area of this peak, integral area of this all multiplicity together, they are identical. The total area of the multiplicity multiplied here and the total area of uncoupled proton are identical, there is no difference at all. That is important point to remember. Only thing is intensity gets distributed when I undergo splitting, it gets divided, 1 will become 2, 2 will become 4, 4 will become 8 like that. And multiplicity of the peaks among the equivalent spins is given by a formula called 2ni plus 1, especially for a weakly coupled spin system. I will tell you what is weakly and strongly coupled as we go ahead further. For coupling among non-equivalent spins and equivalent spin, the relative intensity within the multiplicity is given by what is called the coefficients of the binomial expansion, or in other words it is called Pascal triangle. I will show you what is Pascal triangle when we go ahead further. So, these are the important salient points of J coupling. Every point we can take number of examples and discuss, but this is not the time. I wanted to give you the gist of that. So, you please remember these are the important points. Now, what happens if there are two nuclear spins which are interacting? There is J coupling present between two spins. That is what I mean by interaction through covalent bond. It will split the energy levels. If one proton is coupled to other proton, each of them will undergo splitting, energy levels undergo splitting. In other words, remember in NMR every interaction is mutual. If one is proton A is coupled to proton X is also coupled to proton A. Interaction between the spins are mutual in NMR. Okay. Now, we will see the J split energy level. When chemically non-equivalent spins are coupled, there is splitting of the energy levels. This depends upon number of spin states of the coupled spins. I will tell you what is the spin states now. Each spin will give rise to multiplicity pattern at the respective chemical shifts depending upon the number of spin states available with the coupled spin. A very important point, you will see that. Now, look at this one. There are two coupled spins I will take example. If there are two coupled spins, how many possible spin states we can think of? Please remember in the very first class I told you there are two spin states for a spin of nuclei alpha and beta. One corresponds to the direction of the field, other is in the direction opposite to the field. This is alpha and this is beta, that is what we discussed. Now, there are two spins, whether it is coupled or uncoupled, let us look at the situation. What are the various combinations of these interactions we can think of? Now, spin 1 can be alpha position and beta position, spin 2 can be in alpha and beta position. Now, you have to take the combination. Combination will be like this: alpha can have a interact with alpha, that can be alpha alpha orientation. When this spin is up, this can also be up. When this spin is up, this can be down. When this is down, this can be up. When this is down, this also can be down. So, 4 such possibilities. This is what is called, when both are up we call it as alpha alpha, when both are down we call it beta beta, when one up one down it is called alpha beta, when this is down this up we call it as beta alpha. Like this 4 different combinations we can think of. That means each spin will see other spin in 2 different energy states, okay. And this causes splitting of the energy transitions, splitting of the energy levels, and as a consequence you see multiplicity of transitions. Look at this one. Now, consider the proton A. I consider 2 protons A and X coupled to each other. Now, they have put it in a magnetic field B naught. When proton A can see proton X in alpha position, proton X, remember proton A is coupled to proton X, it can see proton X in alpha position, then it gives rise to, in such a way, a frequency which goes downfield, okay. Because it is orientation of the X spin is in alpha, it orients like this. As a consequence, we are going to get a peak in the downfield with respect to the original chemical sheet position of the proton A. Now, it can also see proton X in beta position, in beta state it will see, that will be orientation like this. Then it will also see another energy state. Because of that it resonates at higher field, it comes here. In together proton A sees proton X in alpha and beta states. As a consequence it has 2 peaks, 2 resonance frequencies, because it sees 2 energy states. The magnetic field experienced with this proton A are 2 different things, one B naught plus small value and B naught plus large some value. So, there are 2 magnetic field it sees, as a consequence you get 2 peaks. This is because of 2 different orientation of the coupled spin. Now, you may ask me a question, what happened to proton X? Identically proton X also behaves like that. Proton X see proton A in alpha and proton A also in beta. As a consequence again you will see 2 peaks here. Essentially it means when there are 2 spins coupled you will get 4 peaks, 2 for A, 2 for X. At the center is what is called the chemical shift of A here, chemical shift of X here. Which is A, which is X is my nomenclature, you can interchange also, no problem. chemical shift of center of this doublet gives you chemical shift of one nuclei, center of this gives you chemical shift of other nuclei. And the separation between this coupled multiplicity pattern, coupled spin multiplicity gives rise to what is called coupling constant. This is called J coupling. Now I am considering two spins and they give rise to that, each of them will become a doublet and the separation is J coupling. Now you may ask me why 2, if I take 3 what will happen? When there are 2 you got 4, it is 2 square is equal to 4. When there are 3 spins, let us say, what will happen? It will consider as 2 cube, that will be 8 transitions you can think of. Okay. So 8 possible energy states, 8 possible energy states you can find out how many transitions are allowed or not based on the selection rule. Or in simple words I tell you, if proton A, M and X are there, this proton A will see this in alpha and beta position, becomes a doublet, then it will see this in alpha and beta position, becomes doublet of doublet. So A will give rise to 4 peaks, similarly M will give 4 peaks, similarly X will give 4 peaks. This is how you can understand how the multiplicity comes. It depends upon number of spin states available for the coupled spin. Okay. So now we will understand multiplicity of the NMR spectrum, how it comes in different situations. Simple rule, coupling of a proton with n chemically inequivalent protons gives, if there are n chemically inequivalent protons, the splitting pattern is easily obtained by a family tree approach. What is a family tree approach? Very simple, 1 will become 2, then 2 will become 4, 4 will become 8, like that it keeps multiplying. This is called a family tree approach, like a fission reaction, and you will see in nuclear reaction. So now we will understand this. Let us say one proton is coupled to other non-equivalent protons, how it will affect. I am considering a situation, one proton is coupled to 2 other non-equivalent protons. Remember, I consider a hypothetical case. I look at proton X. This is a hypothetical molecule. Now this can couple to proton A and proton M simultaneously, both are possible. Whatever the coupling strength, they are different, we do not care, but there is a coupling. Now let us start with proton X without any coupling. Assume there is coupling between this and this are 0. Then how many peaks you expect? Only 1, because coupling strength is 0. Now I bring in the coupling, let us say intensity is 1 for this. I bring in the coupling of this X with A. A can have 2 orientations, alpha and beta. As a consequence, this will become a doublet. Now what is the intensity now? 1 will become half into half, 0.5, 0.5, and this separation is the interaction of strength between A and X, that is JAX, and the intensity reduced to half. Now simultaneously it can also experience coupling with M. M is again in alpha and beta states. Again it will become, each lane will become half. Now what is the intensity? 0.25 into 0.25, 0.25, 0.25, and this separation gives you coupling strength between M and X. This is JAMX, this is JAX coupling. Now you may ask me a question, what happens if I look at A and M, not X? Exactly same phenomena. Now A can experience coupling with X and M in 2 different spin states for each of them. For A will also give 4 lines, similarly M also will give 4 lines. Similar pattern is seen at the chemical structure of protons A and M. Now one proton is coupled to 3 other protons, let us say. What is going to happen? Look at this, this is a proton X. Proton X can couple to proton A. Up to this we already understood. We are going to get 2 lines, again 2 lines, 0.5, 0.25 intensity. Now I am bringing in the third proton, coupling with pre. What will happen? Each of them will be further split into 2 lines. So we are going to get 8 lines. Earlier when one was coupled to 2 protons you got 4 lines. Now when one is coupled to 3 protons you are going to get 8 lines. And what is the intensity? now further reduced by half 0.25, 0.25 and 0.25. Okay. I am sorry 0.125, 0.125, 0.125. So, this is the example of 3 coupled spins A, M and X. A gives 4 peaks because of its coupling with M and X. M gives 4 peaks because of coupling with A and X. X gives 4 peaks because of its coupling with A and M. Remember, the spin you are observing coupled to remaining 2 spins. Now you are observing M, it is coupled to remaining 2 A and X. Now you are observing X, it is coupled to remaining 2 A and M, and each time you got 4 lines. So, totally you got 12 lines. So, for n different protons, when they are coupled to different other protons, the total number of lines at the set of observable proton, one proton that is observed is 2 to the power of 2n minus 1. Now, for example, 3 spins, 2 to the power of 3 minus 1, that is 2 squared. So, it is equal to 4, that is what we observed. For each proton at its respective chemical sheet position, we got 4 peaks. So, in the 3 spins are coupled. If there are 4 coupled, what will happen? 2 to the power of 4 minus 1, 2 cube. So, at the respective chemical sheet position of each proton, you are going to get 8 lines. So, now there are 4 protons coupled, 8 into 4, 32 lines. Here 3 protons are coupled with the 4 lines, 3 into 4, 12 lines. That is how it goes. So, the number of peaks you see at the site of one observable proton when it is coupled to n other protons is given by 2 to the power of n minus 1, and the total number of peaks in the entire spectrum is given by each proton site you get this many peaks. If there are n protons, you get n into 2 to the power of n minus 1 number of peaks. So, that means for 3 spins, each spin will give 4 lines, 4 lines, 4 lines, 4 lines. Now, according to this formula, 3 into 4, you must get 12 lines. That is exactly what you are seeing. You get 12 lines. If you go to 4 spins coupled to each other, you say 2 to the power of 3, 8 peaks you get for each of the protons. 8 into 4, you get 32 peaks. So, use the familiarity approach and calculate. You will see there will be 832 peaks. This is how you identify the number of peaks you are going to get in the chemically inequivalent protons are present when they are coupled among themselves. Now, I will tell you something about what is called active and passive couplings. This is something very important you must understand. We always use this jargon in NMR called active spin, passive spin, etc. Similarly, we talk about active coupling and passive couplings. What is an active and passive coupling? We will see here. Look at this one. I have, let us say I have 5 protons, 1, 2, 3, 4, 5 I circled here. They are all coupled amongst each other, among themselves. Now, I am going to detect proton 1. That means, there are 5 different chemical shifts. I am detecting, let us say, proton 1 which comes here. It is a coupled spin system. A spin system is one where everything is coupled among themselves. Now, I am looking at this. The proton that I am observing is called an active spin. Remember, this is an active spin. When I look at this chemical shift, this is an active spin. When I look at this is an active spin. Then what are passive spin? All the remaining spins which you are not observing, they are passive spins. So, there are, let us say, 5 protons here. I am observing this is an active spin. The remaining 4 are passive spins. So, in this case, now one is a proton which I am observing, that is an active spin, and the remaining 4 protons are called passive spins. So, now we will see what will happen in this case here. Okay. Now, when I am looking at the proton spin, it can couple. See, this proton spin can couple to proton 2, coupling constant is J12. It can couple to 3, J13. It can couple to 4, it can couple to 5. I mean, it need not couple to 5, no problem. Coupling could be 0, does not matter. But all these are called active couplings, because you are looking at the active spin which is coupled to passive spins. They are called active couplings. Active spin coupled to passive spins are called active couplings. Now, these couplings give rise to multiplicity for proton 1. Now, you can understand This is coupled to this, become a doublet, doublet of doublet, doublet of doublet of doublet because of this. It will become 2 lines, 4 lines and 8 lines. This coupling is 0, does not matter, I do not care, but nevertheless this proton coupled to 3 remaining protons which are called active couplings. Now another thing, what about this coupling? See, we have to also see other protons which are active here. See, for example, this coupling is also present. Proton 2 they form part of the coupled spin system. This can couple to this, this can couple to this, this can couple to this, all other couplings are present now. These are called passive coupling. This is coupling among the other spin other than peak of my interest. These are called passive couplings. These passive couplings are not seen at the active site. At this proton site you only see the coupling between active and passive spins, but not among the passive spins. Remember what is active and passive coupling? Active coupling is the one which are going to see coupling between active spin and passive spins. Coupling among the passive spins are called passive couplings, that is not going to be seen here. On the other hand, let me consider this one. I want to see proton 3 and this is the active proton, active spin. Then coupling to this is active. Coupling other than this, they are passive, that is not seen here. This is the difference between active spin coupling and passive coupling, and passive coupling will not be shown at the chemical state of this proton which you are observing now. So, active and passive couplings in homonuclear case, I will take a simple example like this. I consider 3 spin case, 3 protons are coupled, I call it A and M. Now, when I am looking at the A is an active spin. When A is active, these two are passive, correct. So, A will couple to M and X. So, AX and MX are the passive couplings. I am sorry, active coupling is AX and MX, AX and AM, and MX is the passive coupling. Similarly, look at this one, M is the passive active spin now. When M is active spin, AM and MX are the active couplings and passive coupling is AX. Similarly, here I am observing this X is the active spin and couplings are AX and MX, they are active couplings, passive coupling is AM, that is not seen here. You cannot get AM here, you cannot get AX here, you cannot get MX coupling here. So, active couplings are seen at the active spin case, at the site of the chemical state of the proton which you are observing, you see active couplings. So, passive couplings will not be seen, for that you have to go to chemical state of the different proton. Okay. So, splitting patterns are independent of the signs of the coupling constants, that means it does not change whether the coupling is positive or negative, it does not change the pattern of the spectrum at all. So, as a consequence, important point to remember, one dimensional NMR spectrum does not give sign of the couplings. You do not know if you are looking at the spectrum whether the coupling is positive or negative, that information is not available at all. So, you understood what is active coupling and passive coupling like that. So, I think now time is up, I will stop here, I will use some other terms and talk more about the coupling later, but today I am going to stop here. But what did we do today? We started with another interaction parameter called coupling constant, and we understood various salient features of coupling constant, what will happen to the, how do you represent the coupling, it is a scalar property, it is a scalar this thing, it is just a number represented by Hertz, it could be between homonuclear and heteronuclear. One proton can simultaneously experience coupling with other things, and when it interacts with n number of protons, there is a multiplicity which depends upon the number of spin states of the other protons. As a consequence, what is going to happen? Multiplicity pattern changes. So, multiplicity pattern, if you interpret, you know the coupling constants, and what you are going to see, the proton is an active spin and you are going to coupling between the active and passive spins, which is reflected at the side of the active spin. Passive couplings cannot be seen here, for that you have to go to the different proton. So, varieties of information we understood, how the mechanism of splitting arises based on the orientation, the spin state of the coupled spin also we saw. Take an example of the 2 spin, and we know for the chemically inequivalent spins, the number of protons, if there are n protons coupled among themselves, the number of peaks you are going to see at the chemical set of one of the proton is given by 2 to the power of n minus 1, and the total number of peaks you see in the NMR, in the entire NMR spectrum of that molecule when they are weakly coupled. I will tell you what about strong and weakly coupled later, is given by n into 2 to the power of n minus 1. That is the thing we understood today. We will stop here and come back next class. We will continue further. I will introduce more interesting phenomena about the multiplicity pattern, the patterns we are going to get, how we can get different multiplicity, different patterns in the NMR spectrum. Thank you.